Hello everyone, in this video we'll talk about the public key cryptography and its application in encryption as well as in digital signature. Okay, so last time we talked about the symmetric key cryptography and its main issue in distributing the key or in agreeing the key between sender and receiver, especially when both of them never met before. Okay, now it leads to the ideas of using public key cryptography, which was initially proposed by Diffie and Hellman in 1976 and by RSA, Rifes, Samir, and Ade on the year of 78. So in this public key cryptography concept, each of, let's say, Alice and Bob, let's say it's sender and receiver, they have a set of key, basically public key and private key. The public key, it is a key that is known by everybody in the network. It can be, let's say, introduced by the sender itself, okay, or it can be put somewhere, let's say in a registry or something like this. But the private key is a key that is only kept by the owner. It shouldn't be accessible by anybody else, right? Okay, so this is an example of how the public key cryptography is being used in encrypting the message. So let's say Alice wants to send a message to Bob. So it doesn't. She doesn't have to agree on the key to Bob with symmetric key cryptography. So it can simply get the Bob's public key because it is known by anybody else. So Alice can encrypt the plain text message by using Bob's public key. So it is written in this notation KB plus M. And since B has its own private key, so Bob can decrypt the message, recover the message to the original message that is sent by Alice. All right. So yeah, just one note. Although this scheme looks a bit simple, I mean it's not much different than the symmetric key cryptography, but then mathematically it is much more complicated than symmetric key cryptography. So now, having said this, we can compare between the public key and the symmetric key cryptography. They both have their own pros and cons. In public key cryptography, it doesn't have any issue with the key distribution, okay, because there is no need to agree on the key between sender and receiver. But then mathematically it is more complicated than symmetric key cryptography. But then on the other hand, in symmetric key cryptography, it has an issue with the key agreement or key distribution, but then it is much more less complicated in terms of mathematical computation. All right. Okay, so now before we go to the digital signature, I just want to highlight there is one important property in RSA or in public key cryptography, which is, okay, basically this left hand side. This is the notation that we use in using the encryption. Okay, so let's say B or anybody wants to send a message to B. This person can use B's public key to encrypt the message, and then B can decrypt the message by using its own private key. Right. While on the other hand, this will be used in digital signature. So let's say B wants to B wants to sign the message that it is sent. It can use its own private key, and then the receiver of this message can verify whether the signature is valid by using B's public key. All right. So now let's go ahead and take a look at the digital signature and how it is how it is used to ensure the integrity of a message. Okay, so first of all, this digital signature is a bit similar from the handwritten signature in terms of its purpose. So as we know, the handwritten signature is actually to say that this document is really issued or it is signed by the signer. So it's not issued or it's not signed by anybody else. Right. So the same in this digital signature. So let's say Bob signs a document and then it is received by Alice. So Alice can make sure that the document is really signed by Bob. It's not signed by anybody else. and also it is the document. Bob sends this document, not other document. And then there is one more important feature that is not covered by the handwritten signature. This is called the message integrity. So when, let's say, Alice receives the message from Bob, it can and if the message if the signature can be verified, it means that the message has not been tampered, or there is no change in the message. All right, so that's we'll see how it works in the next slides. Okay, so now let's say Bob wants to send a message to Alice, and also Bob wants to make sure that the message is not changed, okay, during the transmission. And then also Bob wants to make sure Bob wants that Alice really think that Bob is the sender of this message. It's not sent by anybody else. All right. So what Bob does, he signs the message by using Bob's own private key. All right, and then Bob sends both the message and its signature, digital signature, to Alice. All right. Okay, so now on the receiving side, Alice receives both the message and the signature, and then Alice can verify the signature and the message by using Bob's public key, and then checks whether it matches. Okay, if the signature matches with the message, then Alice can ensure that basically it is Bob that signed the message and no one else signed the message. Okay, and then also Bob signed the message M and not M prime. All right, and there is one more property in the security, which is called non-repudiation. So in case of, let's say, criminal case, if there is any fraud or something like this, Alice can take the M, the message, as well as the signature to the court as the digital proof. Okay, that can be used to, let's say, to be used in the court. All right, so let's say now Bob sends large documents to Alice. Let's say one long document, PDF document, or maybe one video or one software or something like this. Normally it is very big, and it's completely expensive to sign very big document or big data. So is there any way to make the competition more less expensive? So one method is to create message digest, basically. So what is message digest? So message digest is actually we can apply a message, large message M, with the hash function. Okay, so if you're familiar with the hash function, actually it's a one-way function. Okay, that it is one way because it is irreversible. So it's normally applied in a password. So if you have your password and then it can be hashed. So if someone captured this hash version of the password, this guy cannot reverse it and then to get the original password. Okay, so what normally people do is to brute force the password. All right. So anyway, hash function. There is one more property that is very important. Is it produces fixed size message digest. So for example, like if is 128 bit hash function, then the results, no matter how large the message is, the results will be 128 bits. If we are using 256 bits hash message algorithm, then no matter how large the message is, then we will produce 256 bits of hash or digest message. Okay, so now it is actually just a little bit modification before we take the signature. So now we have the large message. So before we apply the digital signature to the message, first we create hash of this message or the digest by using hash function, and then instead of digitally sign the message itself, we can sign the digest of the message, or message digest. And then we have two things to be sent to the receiver. We can send the message, the whole message, as well as the signature from the message digest. All right. So in the receiving side, the receiver will receive both the message and also the signature. All right. Now to compare both the message and the signature, we have to first apply, or the receiver has to apply the message to the with the hash function to get the digest, and then we can apply this signature, or the received signature, with the public key of the sender to get back the digest, and then compare both of them. If they are equal, then it can be verified. Otherwise, it is not verified. Okay, now talking about the hash function algorithms, there are several hash function algorithms. I think the first one is MD5, is quite popular, but now it is considered as not secure anymore. The one that is used right now is SHA family. It stands for SA. Sometimes people say SA. Standard hash algorithms. The SHA1 or SA1 is 160 bits long. There is also SA156, SA512, and so on and so forth. All right. So now we go to different topics. It's public certification. So before we talk about the public certification, or certificate, basically, okay, we'll see about this simple illustration. So let's say Trudy wants to place pizza prank on Bob. Okay, so Trudy creates an email order. So it sends the let's say it sends a request to a pizza store, but then it says that, okay, so this pizza will be delivered to Bob, and then Trudy, when he sends the email, it acts as if she is Bob. Alright, because nobody knows whether this, let's say, public key belongs to Bob or belongs to Trudy, right? So there is no way to verify whether this the identity of the public key is really belong to anybody. Okay, so Trudy signs the order with her private key. Okay, and then it sends the order to pizza store. Trudy sends to pizza store her public key, but then she says that it belongs to Bob, right? Because there is no way to verify that this private key, public key, belongs to Bob or belongs to Trudy. And then since the pizza stores receive the public key from Trudy, so it will be able to verify the signature. All right, so basically the message is verified. There is no problem with the message, but the problem is the pizza store doesn't know that it's really Bob that signs the message. Okay, so at the end, the pizza store delivers the message. Delivers the pizza to Bob, and then Bob didn't really think that he already ordered that pizza, and he doesn't even like pepperoni, for example. Okay, so this comes to an idea of having a certificate authority. The purpose of this certification authority is to bind the public key to some entity. Okay, so this entity can be a person, a router, or anything. So basically, in practice, it contains the names, and then let's say the company, the address, emails, and so on and so forth. So this is in reality, like for example, when we are establishing HTTPS SSL. So first we have to receive the certificate from the server that we want to access, and then in that certificate, it contains all the information about the servers, okay, the owners, the emails, the address, and so on and so forth. And then what actually the browser does in background, it is verifying that the certificate is actually valid. Okay, so it verifies the certificate to the CA. Okay, so before let's say before we obtain the public key of the server, so first we ask whether this digital signature, the public key that is contained in the certificate is actually valid. How we validate the certificate? We can use the public key of the CA. Okay, so basically, and also in when we talk about the certificate itself, the certificate is signed by the private key of the CA. Okay, so now we have the public key. The public key is put in the certificate, and then both of them is signed by the CA's private key, so it becomes a certificate. Okay, so now if someone wants to verify whether this public key really belongs to Bob, okay, so this guy has to use the public key of the CA's public key, and then it can verify that really, okay, so this certificate is valid and KB plus is really the public key that belongs to Bob. Right, so on the other hand, like if we are using our example, we can verify that this public key is really belongs to the server that we are accessing. So sometimes when we access the websites, we find that there is some warning by our browsers. It says that the certificate is not valid or it is self-signed. So it means that let's say the signer of the certificate is not trusted CA, or the CA is not known basically. In the standard browser, the browser has already collected some public key of well-known CAs. All right, so now let's see how the Alice let's say Alice wants to get the Bob's public key. So what it does is it gets the Bob's certificate from Bob himself or from anybody from somewhere else, and then Alice uses CA's public key to Bob's certificate, and then see if it is verified. Okay, so if this certificate is verified, then it can obtain the Bob's public key. Alright, so that's it about public key cryptography and how it is used in encryption and digital signature. Let's talk about some application about this both symmetric key cryptography and public key cryptography in action in the next videos.